Alright guys, so in this video I wanted to talk about finding the antiderivatives of these functions, or at least getting an intuition as to why the antiderivatives of these functions are what they are, by just looking at the graphs of the functions. Now before I get into how we're going to do that, I just want to say as a little bit of review, that when we're taking the integral of something, and I'm just using sine of x here as an example, really what we're doing is we are getting the antiderivative first of all, right? So we're getting this antiderivative function. We don't know what that is yet for sine. And then in order to get the area under the curve using that antiderivative, we plug in two bounds. So in this case, I said 2 pi and 0. So you would plug in the upper bound and then subtract it from the lower bound plugged in. And this subtraction is going to get you the area between the two bounds. So in this case, it would be the area between 0 and 2 pi. So we're using the sine function. So in this case, what we just calculated is the area all the way from here, all the way up to 2 pi, all the way from 0 to 2 pi. And this would actually just equal 0, because this area over here and this area would cancel. Because if the area is below the x-axis, then it's considered negative. Okay. So that's just a quick review of how we can get the area under the curve. Now what I want to do with that is I want to look at the area under the curve, just sort of eyeball what the area under the curve is. So for example, I could take a point right here, and then I could say, okay, this area over here, this looks a bit like, I don't know, pi thirds. Let's just say I said this looked like pi thirds, the area looked like pi thirds. Then I would say, okay, we know that this is about pi thirds, and we know that this area is a reflection of the antiderivative. It's not going to equal the antiderivative, it's actually going to equal this whole thing, right? It's going to equal this whole thing. So we're saying that pi thirds equals, let me just write that out, would equal f of whatever x value it is minus f of 0, right? But the thing is, we're actually just going to graph the areas. And the reason we can do that is because if we just keep bounding along, if we keep taking values along this curve, and we keep getting the areas between whatever point it is and 0, then, and keep graphing the areas, right, from 0 to whatever point it is. So for example, here I would graph pi thirds, which is around here. And then over here, the area is increased a bit, so I would put it over here. Then I'd just keep graphing it, and that way we're graphing the area under the curve. But this area under the curve, in this case, is going to reflect the antiderivative function. And the reason for that is we're always using the same lower bound, right? We're always getting the area between some x value and 0. We're always using 0 as a lower bound. So that means that this f of 0, because it's not changing, this f of x is the only thing that's changing. So if we graph the area under the curve from 0 to whatever value, then that curve that we graph, that area under the curve graph, is going to be a reflection of what the actual antiderivative looks like. It's not going to actually equal the antiderivative, but it's going to reflect what the antiderivative function looks like. So using that, we can find out what the antiderivative function looks like, its pattern sort of, and then we'll see if there are any functions that match that graph. Okay, so let's get rid of this, and let's actually start graphing it. Graphing the area under the curve. Okay, so let's start with pi halves. So let's say right here, what is this area under the curve going to be? What do you think? Well, I think it's probably going to be about pi thirds, let's just say. Just eyeballing it, it looks like pi thirds. The reason I'm saying pi thirds is because we know it's going to be less than pi halves, because this full rectangle is going to equal pi halves times 1. So it's going to be less than that, so I'm just going to say pi thirds. This might not be accurate, but let's just say that it's around pi thirds. And pi thirds is going to be a little bit more than 1. So let's graph it right over here. Actually, let's get rid of all the labeling. Okay, of all of the, yeah, okay. All right. So pi thirds over here. So I'm just graphing this area under the curve graph. Now let's go to pi. At this pi value, it's actually going to be double the value that it was before, right? Because these two areas are going to be equal. This area over here, they're equal. So we'll just take this value over here, we'll double it. I think that's about twice this size. So this is going to be 2 pi thirds, right? And this is all just based on estimates, right? Okay. Now let's look at 3 pi halves. 3 pi halves, well, now the value is actually decreasing, right? Because we have all of this negative area over here. And it's actually one of these halves of the positive part and this half of the negative part are going to cancel. So we're only going to have half of the positive part left. So we're going to be back at pi thirds. Okay, and then as we go on to 2 pi, we've actually got an even more negative area, and that is going to result in just 0. So now we're at 0 now, okay? Oh, and I probably should have graphed this before, but the value at 0 is going to be 0, right? Because there's no area filled yet. Okay? So we can already see it's kind of like a periodic function. It's going back and forth between up and down, right? And then over here, we're going to be back in the positives, right? It's going to be this area right here. All of this area over here canceled. Because remember, it's from 0 all the way to this point. So this would cancel. So we're back at pi thirds. Okay, and I'm pretty sure we've graphed the entire, well, actually, let's just do one more. So then 3 pi would be 2 pi over 3. Let me just make some space. Okay. 3 pi, 2 pi over 3. Okay. Now let's look at actually how this is going to increase. Is it just going to be linear, or what's happening? Well, we can see that the rate at which, from 0 to pi halves, the rate at which the area is increasing is actually going to decelerate. And that's because we can see we keep adding slices, right? Theoretical slices, I guess. And these slices keep getting taller and taller. Oh, sorry, did I say decelerate? I meant accelerate. Sorry. Yeah, the rate at which these are at the area is increasing is accelerating because they're getting tall. These slices are getting taller and taller. And if they're taller, then the area that they're adding is going to increase. So we can draw an accelerating line. Now over here, it's going to be decelerating, right? Because the slices are getting shorter and shorter. So it's going to look a bit like this. Okay. And then when you are at pi, well, now it's going to be decreasing, but right, we're looking at the pink line. By the way, just to make that clear, we are doing the sine function right now. Yeah. Okay. Now it's going to start decreasing. These slices are getting bigger and bigger, but it's going in the negative direction, right? So that means that the rate at which it's decreasing is going to accelerate. Okay. So at first it's not going down by much, but then it's going to increase how much it's going down. Okay. And then it's going to be the opposite. because the slices are getting shorter and shorter in the negative direction. It's going to decelerate, and then it's going to go back up, and then it's going to decelerate once again. Okay. So we definitely see what looks to be a cosine, sine, or sine function, right? It's the same sort of periodic function, but it's definitely not equal to one of those, right? And this is also keeping in mind that this is not actually the graph of the antiderivative. This is just the graph of the area under the curve. It just reflects what the antiderivative's curve looks like. Now, we can look at this and we can say sine or we can say cosine, right? We can say that this is either going to be like some derivative of sine, like something that's based off of sine, or it's something that's based off of a cosine function, right? Okay, so are we going to say that this is a sine function or a cosine function? Well, we'd actually say that this is a cosine function. And the reason for that is it's really, this curve is really just negative cosine, right? I mean, obviously it's been shifted up a bit, right? It's been shifted up, but that's just because of the minus f of 0, right? Because remember, this is a representation of the area under the curve as a whole, so this whole thing. But it has the same shape as a cosine function. It has the same shape as a negative cosine function, sorry. And that means that it's probable that this function, f of x, is just minus cosine of x, right? Not this function, but the antiderivative function. Right. Now, the reason it's shifted up is because of this f of 0, okay? Now, you might be thinking, okay, but you could probably represent this antiderivative function as a sine function too. And you could, but what that would look like, right, because if this was just shifted over a bit, if you just changed you could change the sine function to match this graph. You could do that. But it's a lot more complicated to do that than just put a negative sign in front of the cosine function to represent this graph. So that's what you do, even though this graph could be represented by a sine function, by some change to a sine function. But yeah, so it turns out that the antiderivative of the sine function is actually minus cosine, okay? Or I should write dy dx in this context. So dy dx, that's what the sine function antiderivative is. Okay. Now let's actually just get rid of this graph, or yeah, let's get rid of this graph and points on it. Okay, yeah. Okay. Now let's look at the cosine function and see what it will look like. Well, let's start with pi halves. At pi halves, it's going to have this area right here, right? It's going to have this area here. And I'd say that looks a bit like pi thirds again. So let's just graph pi thirds, which it's already graphed because of what I did before. As we go on, it's going to double, so then we're going to go 2 pi thirds. Or sorry, I'm looking at the wrong graph. As we go on, it's actually going to get to 0 because we have negative shaded area, and these two areas are going to cancel out. Okay, so we're going to get to this 0 over here. So 0. And then 3 pi halves, we're actually going to go negative, right? We're going to get a negative value. It's going to be negative pi over 3. Let's look over here. Negative pi over 3. Negative pi over 3. Okay. And then we're going to actually get even more negative, right? Because I mean, I keep looking at the wrong graph. And then we're going to, remember, we're looking at the blue graph. And then we're actually going to get positive. We're going to approach 0 again, right? Because this shaded area is going to cancel out with this shaded area. Okay, and then we're going to get positive again because we have this positive area. So we're going to go back to pi thirds, positive pi thirds. Okay, so we have a sufficient amount of points just for this, just for this quick back the napkin thing, graphing. So let's, is it going to be accelerating or decelerating as it approaches pi thirds? Well, it's actually going to be decelerating. And the reason for that is because the slices are getting smaller and smaller and smaller. Okay, so it's going to be decelerating. And then it's going to be accelerating because, well, as it approaches the negative values, so. But, yeah, it's going to accelerate in the negative direction, let's just say. Okay. And then it's going to be decelerating because the length is getting smaller. So then, and then it's going to repeat that. Okay. Yeah. And you might be able to see that this is pretty much just the sine function, right? Or this pretty closely just traces the sine function. So we just say that the antiderivative of cosine is sine. Okay. Actually, let me write all this out. This is minus cosine, and this is sine. Okay. Okay, and then what is tan going to be? Well, okay, actually. Okay. And to get rid of all of this, can I get rid of the graph that I just drew? Okay. Okay, there we go. Sorry about that. Now let's look at the tangent functions. So let's graph the area under the curve for tangent. So right here at 0, it's going to have a value of 0, right? And then as we go on, right, it's going to get really, really big. And the reason for that is the function itself is approaching a really, really big number. So the area under that curve is going to approach a really, really big number. So I'll just put an arbitrary dot over here to represent a really big number. But then when we go back down to the tangent, to the next line, I guess, then we're going to have a negative area under the curve, right? So we're sort of going to be starting to approach 0. So we're going to approach 0 again, and at this point we're going to have actually the value 0, because the area under this curve and the area under this curve will cancel out completely. Okay, and then as we go on, we get a positive value again, right? So another positive value, and then it's going to keep repeating that. We're going to go back down to 0 over here. Then we're going to go back up to a really high number over here. And it's kind of interfering with what I drew up here, so I'll just erase it. Oh. Okay. Just get rid of this. Okay. Now what is it actually going to look like as it approaches this? Is it going to be accelerating or decelerating? Well, it's going to be accelerating, right? Because the height of these like sort of slices is getting bigger and bigger. So draw sort of an accelerating line like that. And then over here it's going to be decelerating because the way that the amount it's going in the negative direction is going to decelerate, right? Because the slices are getting smaller and smaller. Okay. And then we're going to get back up here. It's going to be accelerating. Same reason as before. And then we're actually just going to get these these lines over here. So then, and then if you were to look at it in like a sort of a small, like a from far away, you just have a bunch of these things. And you might remember, but the secant function looked a bit similar to that. The secant function, I think it was the secant squared function. But they both have similar patterns, I guess. So we know that secant is based off cosine. So these graphs we know are going to have something to do with cosine because they look really similar to secant, which is based off of cosine. So in other words, they look like they could be based off of cosine. Now the question is, how are they related to cosine? Well, it turns out that they're actually equal to the natural log of cosine. Okay, that's the antiderivative for the tangent function. Now keep in mind, what I graphed is not the ln of cosine of x. It's not the ln of cosine of x. It is actually this is actually the antiderivative. We're just looking at this graph because we know that it will have a similar pattern to what the antiderivative is. So it's going to be the ln of cosine of x. And what ln does is it basically says, just as a reminder, it takes in an input. In this case, it would take up the input cosine of x, and it would say e to what power, e to what exponent is input. So in this case, it would say e to what power is e to what exponent is equal to cosine of x, right? And then it would output that. And then for every value, it would output that as the y value. Yeah, but that's basically what this function does. Yeah, so that's what the function is going to be. It's going to be the ln of cosine of x, the natural log of that. So natural log of cosine of x. Okay. So that was just looking at graphs and looking at their areas and looking at their slopes to find out what their derivatives and antiderivatives patterns are, and then relating it to functions that we know have those patterns in their graphs. Yeah. So this was in no way a proof of the different derivatives and antiderivatives. This was just to give you sort of more of an intuition as to why these functions have the antiderivatives and derivatives that they do. Okay, that pretty much concludes this video. Thank you.